lesson 2, which is about virtualization and lightweight containers. And I think this is going to be one of the key technologies that are going to be used from now on. We're already using them, in fact, aren't we? So look at what the principles are of virtualization, and then some changes which were made to Linux to support it in an interesting way, and then start looking at container technology and Docker. And I think Docker is something that's going to really take off. And so what we'll do then is spend the rest of the session looking at various aspects of Docker and getting it ready. So virtualization is very important because it solves certain issues. So we've got the traditional architecture where you have a computer with an operating system and probably one or more applications running on the operating system. So with the virtual organization, we have the hardware, then we have a piece of software which is actually usually an operating system in a very cut down sense. It's usually Linux based. And that provides a virtualization layer, and then we can have a number of operating systems running on top of that, which are unaware of each other's existence, and each operating system, of course, can have its own applications. So we have a problem when it comes to things like versioning. You've got an application that runs on different platforms, different operating systems. It might run on Windows, it might run on Unix, Linux, OS X, one of the different ones. And it might run on different versions of operating systems. So, for example, some software doesn't run on certain versions of certain operating systems. Okay, for example, Docker doesn't run on Windows, which is anything less than version 10 at the moment. And there's also dependencies on different libraries, and this is what causes a lot of problems. If you've got an application which is dependent on a third-party library, then you add a second application which is dependent on the same third-party library, and one of them needs a later version of the library, it could break the first one, which is a real problem. Then you start having different versions of libraries, which starts to get incredibly messy and difficult to manage and maintain. So otherwise, the alternative is to have lots of separate environments, and that's not really practical because you're going to have hardware resources used up for each one, and then how many combinations of operating systems and libraries you need to have that. And setting up an operating system with the appropriate libraries is actually very time consuming, and we don't really want to spend all of our time configuring machines. So when you get to large organizations, it gets even more complex. So for example, within a very large organization, you'll have requirements for, say, admin staff, and then for operations staff, and then for developers. And they'll all be different. They want different combinations of software and they need different access. And if you remember the least privilege principle from security, you don't want to give everybody the full access that, say, a developer needs when they don't actually need it because of the issues that raises. And developers require higher levels of access, and they also require very specialized tools which the others will not need at all. So then when you want to, say, apply a patch to Windows or something else, or update a library or some software, it gets very difficult. So, and then doing things like meetings, it gets very complex there because you need a particular environment in a meeting environment, which is not going to be the general case, and you don't want to start moving computers around. So we had the multiple boot machine, which has been around for quite a long time, where basically you have a separate disk or disk partition for each operating system. There are some issues with that. You need some kind of boot manager to deal with it. There are the Linux ones like Grub, which are around and they do the job very well, but they have fairly complex configurations sometimes. And the problem is, if you've got Linux running alongside another operating system, no matter what it is, it can read the other disks because Linux can read more or less anything. So bypasses all the security of the underlying operating system if Linux is running alongside it, and you access its disks as just raw devices, for example. So we have the concept of virtual machines. Now, you might think they're fairly new, but they're not. They've been around since the 1960s because the big mainframes of the 60s use virtualization to do multitasking. So typically every single program more or less ran in its own virtual machine. And each program appeared to have full access. Since then, we've had a number of software packages come along which do that. There are a number of them that are still around. VMware has probably been one of the most important players in virtualization because it started in the late 1990s and it's still going strong for virtualizing the 80386 architecture or 8086 architecture. So what's the advantage of a virtual machine? Well, the great thing is you can set up a complete environment which is completely isolated from the others, with the exception of that Linux thing I mentioned. If you want to replicate a virtual machine, you simply copy it, and you don't have to do any installation on the other machines other than just copy the image across. Several operating systems can run at the same machine at the same time as long as there's enough hardware resources in terms of CPU and memory, etc., to do that. And they get rid of the need for multiple boot machines, because if you wanted to have a multi-boot machine, you had to shut down your operating system and start up the next one. And with a virtual machine, you just simply fire up another virtual machine on your current operating system, and that's fine. We don't need multiple boot machines. We can have virtual machines which we just fire up, and they just work. Virtualization software, the software that does the work is called a hypervisor. And what it does is it provides the guest operating system with access to what looks like the full hardware of a computer. Sometimes it is the real hardware, and sometimes it actually emulates the hardware. And this is actually quite useful for certain environments. One that I previously had very serious problems with was Solaris, in that running Solaris on a PC, it always had problems accessing the video, and it was a real nightmare to get it configured. If you run Solaris in a virtual machine, the problem goes away because the virtual machine provides an emulated video environment which you can easily configure Solaris to use. That's the advantage. And there's two types of hypervisor, although the distinction is getting a little bit vague at the moment. The type 1, which is also called a native or bare metal hypervisor, is basically a piece of software that's installed directly on the hardware. It's usually based on Linux. VMware was originally based on a modified Linux kernel. And then the guest operating systems run effectively as processes on that host operating system, which is the hypervisor. This is the approach used for the high-end servers. So if you go to a big data center with huge servers in there, they'll be doing virtualization, and they will be using these really high-end ones like the Oracle VM Server, Citrix, and so on, VMware, ESX. All these are quite expensive products, but they enable you to run a large number of virtual machines on a large piece of hardware seamlessly. So that's the principle there. You've got the hardware with the hypervisor sitting on top of it, and then the individual operating systems sitting on top of the hypervisor with the applications running on the operating systems themselves. So now we go to type 2, which is a hosted hypervisor. Basically, what happens is the hypervisor software runs as a single process on a normal operating system. It doesn't matter which one it is, as long as it supports it. And then what it does, you run a virtual machine on the hypervisor, but what it has to do is emulate some of the calls from the guest operating system onto the host one. And it might have to do some clever tricks to make it look like the guest operating system's got access to the hardware. And that includes things like VMware Player, VMware Workstation, and Oracle VirtualBox are type 2. Right, so then the thing is that the situation, this is the type 2 situation, and just to have this extra layer where there's an operating system underneath the hypervisor. So in terms of the technology, actually the idea is not new at all, as mentioned in the 1960s, but when the Intel 80386 came out, which was quite a long time ago now, I think, can't remember the exact date, it had a very interesting approach. It started up, when you fired up the CPU, it looked like an 80386 processor. And then if you issued certain instructions and set up a data structure, you could put it into what was known as protected mode, where you had the full power of the 80386. But when in protected mode, the 80386 could create any number of virtual 80386 environments. So you could actually do that. I remember once in the early days of the 80386, I had a Windows machine, and I wrote a little assembler program where I pushed the 803.86 into a protected mode and dumped the whole of Windows operating system into a virtual 803.86 environment, and it worked perfectly. And I had a little console at the bottom where I could communicate with the actual protected mode CPU at the same time. Then what happened was that the chip manufacturers, such as Intel, realized that this was going to be an important technology, and they added instructions to the CPUs which enabled virtualization to be controlled more easily. And what effectively happens is that these special instructions can be utilized to effectively allow multiple operating systems to share the same hardware without knowing about each other. So it's really clean stuff and neat stuff. And this extension was made to the extended page tables, which solved a big problem about memory management. And that greatly opened up the scope for doing really effective virtualization. So what that did, because of the CPU instructions, it blurred the distinction between a type 1 and a type 2. Because if you switch the virtualization on, now that's required, if the CPU supports it, which not all CPUs do. If you go to the Intel site, you can find out which ones do and which ones don't if you've got an Intel chip. The virtualization is normally disabled in the BIOS by default, because if you switch the virtualization on, a piece of software running on an operating system on the processor could actually switch on the virtualization and take complete control of the machine, which is a security issue. But if you switch it on, which is a good idea if you're going to be running virtual machines, what happens is the hypervisor, say like VMware Player or whatever you're using, will grab control of the CPU and put itself into a particular sort of ring of the CPU mode of operating. And then effectively all the operating systems, the host and all the guests, can use the real hardware as if it was just they were the only ones on the machine, which is really neat stuff to have. And you've also got the Linux kernel, KVM, and the FreeBSD Hive. They always do this as well. So effectively, you run a program on a host OS, and it turns it into a Type 1 hypervisor, effectively, where the actual software becomes Type 1, and the OS can run. Two OSs or more OSs can work seamlessly together alongside each other without knowing about each other. So, yeah, virtual machines are good. We use them extensively. Many big organizations, your desktop will be virtualized. So what you'll have at your place of work will be a thin client, which is usually a cut-down Linux machine. And it will go and fetch your desktop from a data center somewhere, which will be running on a server. And it has that great advantage. I love it, where you're sitting at your desk and you've got you're logged in and you've got all your windows laid out as you like them. You go to another desk or to a conference room or something like that, and you just pull your whole desktop over, and it's there as if you just transported your original machine. You get the same desktop layout and everything. It's really neat. So but the virtual machines are full operating systems, and that means you have to do an installation. When you start up the virtual machine, the virtualization software, you have to do an installation of the OS from, say, an ISO image. And then you have to install all the application software on top of it and configure it, which is quite time-consuming. Though once you've done it, you can clone it any number of times you like. Then you've got performance issues. Memory is usually the big one. If you've got a machine with relatively small amounts of memory, you'll find that the host operating system will grab some of it and won't leave enough for the guest, which is a bit of a problem. There's a particularly nasty problem if you, say, have a 32-bit Windows machine running on 64-bit software and you try and run a 64-bit guest OS. It may work if the instructions are enabled on the CPU and they're supported. It is possible to do it. But the problem is that the 32-bit host maps away some of the memory for things like video and doesn't leave an awful lot left for the guest. So it's not a good idea. If the host is 64-bit, then the memory issues go away because it can address vast quantities of memory. Also, the virtual machines are huge. It's not unusual for it to be sort of tens of gigabytes, and that causes problems transferring them across networks. So there are ways of doing it. The Typical way that I've done it in the past is to use a program like 7-zip, which has got the capability of doing this, to compress the virtual machine and break it up into small chunks of a certain size, and then you FTP or whatever the chunks across to wherever you want to get it to. Because typically a virtual machine consists of a large number of files. They will typically break a large disk into 2 gig chunks as well, the virtual disk, so that for convenience. But say the transferring across the network is a real pain. Even from things like USB devices, they can be very big images. So just to make sure we know what we're talking about here, there are certain terminologies which are sometimes confused, and just to make sure we know what exactly is going on. Multitasking is basically several programs running at the same time on the same operating system. That's been around for quite a long time, fortunately. We've now got the situation where our processors are quite complex. We've got the situation of Moore's Law, where the speed of CPUs doubles every so often. But we're hitting levels now where we can't add much more functionality to an individual chip, because we're starting to get geometries down where quantum effects start to come into effect, where you don't know where the electron is, so you can't control it. So what's happened now is that processors have more than one. When you buy a CPU, it's got more than one actual CPU unit on the same chip. So you've got a multi-core system. You've got one chip with, say, 4 separate CPUs on the same chip. And typically the CPUs, the cores themselves, I use the word core for an individual processing unit rather than the actual chip itself, the central processing unit chip, which may have several. Each individual core typically has several instruction pointers, so it can execute 2 or more programs concurrently on the same core, and that's hyperthreading, which most CPUs these days have got 2 hyperthreads per core. And then we've got virtualization, where you've got a complete computer positioned in some way, and it acts like a separate computer, which is a fancy way for saying you're running a virtualized virtual machine, several virtual machines on the same computer. Okay, so that's the basics of virtualization. As I say, it's been around for a while, it's good stuff, but we're going to go into a more interesting realm now. So, the question, what is Type 1 virtualization? Yeah, I'm seeing a lot of A's there. It's Type 1 or native or bare metal, which is installed directly on the hardware. So now what we're going to do is look at what happened to Linux in terms of virtualization, this led to something really quite useful. Right, so the problem with handling software installation and things is that if you have multiple applications on the same machine, which we mentioned earlier, you can get dependencies which may clash because they require different versions, and then you can't run 2 versions of the 2 different applications on the same same computer, same operating system, which is a bit of a nuisance. So dependencies make it even more difficult. You do an upgrade of a piece of a library software and you potentially break every application other than the one you updated for. When you remove an application, what do you remove with it? Do you remove its dependencies? Is something else using it? We don't actually. It's not easy to find out sometimes. Although the package managers like RPM and APT help you with this process. But when you could often get a piece of software left on a computer which are no longer required, taking up space, and potentially causing a security problem or some other issue. Can the installation be reversed? Say RPM and APT do help with that, but they do have some rather nasty dependency issues. Sometimes it's very hard to install or remove software with using these tools because of the dependency issues. Dependencies are really a bit of a nightmare. Now we have the concept of a Unix jail. It's a rather interesting term to use for that, a jail. And you heard the concept with iPhones of jailbreaking them. Well, that's the same idea, because effectively when your mobile phone applications, particularly on iPhones, the applications are effectively in little jails where they can't get out and talk to each other easily together. They're fairly self-contained. So Unix has been able to do this for a long time. There is a chroot mechanism for confining a process to a restricted area of the file system. It's very commonly used. Like, for example, if you install a server like a name server or a web server, what you'll do is you'll restrict that server into a particular directory structure underneath the root of the file system, so that if something goes wrong and maybe there's some kind of security attack on the server, then it limits the damage that server can do. As it can only access a small part of the file system, it can't actually interfere too much with other processes. But it is possible to get out of a chroot jail. In fact, it's not difficult at all. If you've got root access, you can do it by creating a subdirectory and doing a series of CDs. You can get yourself out of the jail. It's not a big deal because the chroot mechanism is usually only used to restrict applications to certain parts of the file system, and they're unlikely to be able to invoke that mechanism because they will typically run as a non-privileged user. But now what we've got is the idea of container technologies. And now we can make the secure jails, which is much better. And this enables you to do a thing called operating system level virtualization, which is very much a thing which is getting popularity these days. So what happened is in Linux, there's a series of namespaces were defined, and there's a number of them. And what happens is that a namespace wraps some system resource like CPUs or memory or I/O, networking, with any of those features. And then what you do is you put processes into a particular namespace or a set of namespaces. And then what happens is the processes seem to appear to the process that they've got their own instance of some global resource, but actually it's not necessarily the full set of the resource. And it's an important thing for this containerization technology. And the thing is, you can move the processes around. So you can create a new process and put a new namespace when the process is created, or you can move a process around between namespaces and it will see a different set of resources, which is quite powerful. So as you can guess, what's going to come up is that a piece of software will control these resources, these namespaces, and move processes into them so that keep them separate. Linux provides a number of namespaces. The C group, which we'll look at in more detail in a moment, which is called a control group. We have inter-process communication. So that's things like sockets and various things that have a shared memory and things like that, which enable processes to talk to each other. We've got network devices. We've got disks, effectively mount points where you're connecting file systems together. We've got namespaces for process IDs. Now that's pretty key as well, which we'll see later on. And also namespaces for users and groups within the operating system. And there's also things for like time sharing, hostname and NIS naming at the UTS ones. So what are control groups? Well, it's a mechanism which was started by Google in 2006 because they wanted this kind of concept of containerization. So they started making changes to the Linux kernel, which the Linux kernel team obviously liked because they integrated it into kernel 2.6.24 a couple of years later. So what happens is that you've got a control group which associates a set of processes with a set of subsystems, which typically a subsystem is a resource controller which manages resources. Okay, so you've got the control groups will control, say, the number of CPUs. You have one control group which has, say, 4 CPUs, another one has the other 4. You've got memory can be partitioned into other control groups, and each of those can have a set of processes in them, and those processes which are in those control groups will only see the resources which that control group gives them access to. Control groups or C groups are hierarchical, and so you could attach hierarchies to things. If you've got a parent with a child C group, the child inherits the properties from its parents, and effectively each control group hierarchy is a partition of the processes. So basically a set of processes in one hierarchy is completely separated from the set of processes in another hierarchy. So every process belongs to one group, and the child process starts in the same one group as its parent, and you can move them around if you wish. So, just as an aside about Linux processes, or Unix processes, nothing much different there. So, the Linux processes are hierarchical. Every process has a parent process. And when a child process is created, it gets a copy of its parent's environment variables, signal handlers, and open file handles. The root of the tree is process number 1 always. It's usually a program called init, but it doesn't have to be. And the process number 1 is started directly by the kernel, and process number 1's duty is to own and create other processes. So ultimately every process is owned by init. If a child process's parent dies, it gets a new parent, which is init usually. So bringing all these things together, we've got the idea of containers. Operating system level virtualization. So what happens is you have an operating system. It'll have a single kernel, and then you can add these containers at any time or remove them, and they basically get a subset of the resources available on the machine, and they run completely independently. Typically a container is a self-contained file system. It's usually a very cut-down version of a flavour of Linux. And some of them, like Alpine, which we'll be looking at later, is very, very cut down. The image is a matter of a few megabytes in size. And what happens is that you build this file system, and you then put your applications on top of the file system so that you've got, say, something like a server. If you want a database server, you put the database software on top of the cut-down file system. That becomes a container. Then you fire up the container, and that database is available for use. And as long as the distribution on the file system inside the container is compatible with the running kernel, everything's fine. So it's lightweight and really good stuff. I'm using it extensively these days because it's so much easier than having a virtual machine hanging around. You just fire up a container, leave it there as long as you want, then just shut it down, get rid of it when you finish with. So it's the very light operating system level virtualization is very lightweight, and a lot of cloud environments use these things. It's a good way of doing virtualization without the full operating system being required. So the virtualization, you require a set of tools. You need the virtualization subsystem to manage it. You have to create a control group hierarchy for each container, and then mount the container into the regular file system, and then run a program, and using the chroot mechanism plus the control groups to restrict it. And that's basically what it's all about. So the containers are jails. They're a little overhead as the kernel implements the container effectively. There's a number of them about. So we said chroot's been around for ages. There's the FreeBSD jail's been around for a while. Where it started to get interesting was with the Linux container LXC command, and later the LXD, which basically a full virtualization layer, hypervisor built on LXC. And now we've got Docker. And Docker is the leading suite of tools for managing containers and creating containers, and it's gaining a lot of at the moment. So we're going to use Docker quite a lot because it's a great way of doing things. It's there's a lot of containers out there which are ready-made, and you can just pull one down and use it. And you can make your own very easily. So how does this kind of thing work? Well, it's really quite neat. There's Linux and the various flavors of BSD Unix have had a thing called a union file system for some time. Now, what the idea is that a normal file system, say a Unix file system, you have a directory structure, and then any directory in that directory structure can become a mount point, and you can mount an external piece of storage onto the directory structure, and it becomes part of the extended file system. But the thing is, when you mount a file system in Unix, if there was anything inside the directory we used as a mount point, that content disappears. It's not deleted, but it's just invisible, hidden behind the mount process. The union file system enables you to overlay file systems on top of each other. And so they're called branches, where you have directories and files, but you could take one file system and layer another one on top of it, and effectively be the union, as in the set union, of the two file systems. And there's various priorities and things, so same path directories are merged, and if files have the same name, the priority decides which one's visible and which ones are hidden behind the other one. So that's quite a neat mechanism, which makes containerization even more interesting. So the idea is, one of the ideas is you can overlay a writable file system over a read-only one. So things like Knoppix have been doing this for a while. You have like a DVD image of a version of an operating system, and when you run Knoppix, what it does is it fires up the operating system on the DVD image, which is obviously read-only, and then provides a writable layer on top of it. You can access it, or you can write to it, and it's from a memory stick, for example. So you have the idea of layered images, and each layer is typically a set of actions, basically installing software, adding software, making configuration changes, and each of those could be a layer on top of the system. So, and the advantage of that, of course, is that when you do that layering, if something hasn't changed, you only need to change the layer on top. So you can keep the base image doesn't need to change, and then you just change the layers and keep each layer separate, and then merge them all together when you come to build the final image. So let's have a look at Docker. And this is basically the Docker container management tool. So what is it? It's basically it's a container platform. It enables you to create containers, run images and things like that. And it's basically each container runs typically one application, is the idea. A container can run multiple applications, that is allowed, but the kind of philosophy behind it suggests that every container should contain a single application and have a very, very minimum implementation so that there's no interference between different applications. So, Docker container consists of a base Linux operating system, which is basically all the tools and utilities needed to operate a Linux environment. So you'll have all the tools like ls and ps and the ones that you're going to need. But what you won't have are any of the boot mechanisms, processes or scripts, because there isn't a boot mechanism, and anything else that's required, any packages that are required to operate. And so it's a good jail. You can't get out of it. We don't know of anybody that has got out of one yet. It might be possible. And what we do is we start off with an image, which is just basically a big file, or maybe a not too big file, and then the image becomes the runnable container. And so outside you've got Dockers, you have many containers, you've got the operating system and kernel and anything else. Docker is just an application that runs on your operating system and enables you to run containers seamlessly as standalone applications, which are completely isolated from anything else. So Docker is traditionally Linux. It was for a long time, it was only supported on Linux until fairly recently, because it needs the functionality from certain versions of the kernel, which is anyone after the technology was enabled. It requires a 64-bit installation and at least a 310 Linux kernel. And it'll run on most flavors of Linux, not necessarily easily on all of them. For the popular ones such as Debian and CentOS and Ubuntu, it's pretty easy to get it running. Though there are some issues with the CentOS version. I found some problems. And you can get it as an RPM or an APT package and just install it, or you can download from Docker directly as a binary version. For some versions of Linux, you need to do that, use a binary version. If you go to the Docker website, it'll tell you what you need to do for your particular flavor of Linux. Docker for OS X came out fairly recently. It was earlier this year. It now runs natively on OS X, which is good. And you just get a DMG package, which you just install it. It's built on a hypervisor technology. It only works on fairly recent Macs, so it's got to be at least a Mac 2010 because it needs the support for the memory management within the CPU. And earlier Macs didn't have sufficiently late versions of the processor that would supported this technology. It requires a fairly recent version of OS X, 10.10.3, and at least 4 gigs of RAM, because it does use up some memory. There is a problem with the OS X version, which was very frustrating when I was working on this material. There has been a problem that Apple and the Docker people have got an issue communicating about networking. So when you install Docker on OS X, which is what I'm actually running it on, you can't do proper networking because Docker is not capable of creating the right network device to be able to communicate externally. It's not the end of the world. You can still use Docker on OS X, but you can't do certain things where you've got containers spread over multiple hosts. There's also a version for Windows. It only works on the very latest versions of Windows 10, though they said they might support earlier ones. It also requires a package called Hyper-V, which is a virtualization package to work. And it does the things and virtualizes the environment so that you can run effectively Linux stuff on Windows. So it has to effectively look like a Linux kernel in some respects. VirtualBox for virtual machines cannot be run at the same time as Docker because the Hyper-V package and the VirtualBox application are incompatible with each other. They can't work together. So if your OS is not supported, there's a thing called Docker Toolbox, and Docker Toolbox is what you had to use on OS X and Windows before the first part of this year when it was finally released. What it is, it's a virtual machine. It uses VirtualBox, and it's completely packaged, a virtual machine running a Linux operating system which has got Docker installed on it. And so you just run that as a normal virtual machine on your operating system, and then you've got Docker, which can then run other applications. Docker Engine is the key part. So Docker has got a number of components, as we'll be seeing, mainly today, but there's another section on another aspect of Docker in a later lesson. It's client-server. You've got basically a background daemon process, which does all the work, and it's got a RESTful API. This normally by default works over a Unix socket, so it requires the API, the client program, to run on the same machine if you've got it on the Unix socket. It is possible to make it listen on a TCP IP port, and then you can have remote clients to the Docker server. This is one area where you can't work on OS X because if the server's on OS X, the client can't connect to it from another machine, but you can go the other way. So the server is the Docker daemon, and what it does is it manages the containers. So it can go and fetch them, it can build them, it can run them, and it can put them somewhere else. So the containers themselves, where are they stored? Well, there's a number of places. Docker Hub is a repository, a set of repositories up on the cloud, and that enables you to get images of a vast number of things. There are Docker images for all of the major distributions of Linux, and they've got multiple versions of each of the distributions of Linux. They're all cut down. It's also got many, many applications. So if you want, say, a MySQL server, there's a container up on Docker Hub which has got MySQL running on top of some flavor of Linux, and you can just pull it down and run it. And any other application which is popular. So if you want a Jenkins CI server, continuous integration server, you can just pull one down so you don't have to configure your own. And these things are pretty neat actually, because what they're configured in such a way that if you specify certain options when you run the image as a container, it will effectively configure itself. So as we'll see in the next lesson, if you pull the MySQL container down, you can fire it up in a way that it creates a database and a user. And then you can also fire it up when it's been configured and it's got an existing database and users. And you can also fire it up as a client and access another container which is the database server. So they've done quite a lot of work on making this stuff really user-friendly. You can also have private images. You can create your own images. And in fact, Docker keeps its own collection of images locally, so it doesn't have to go fetch them all the time. And there are other places where you can get images from other vendors. So an image is a template, and say it's usually a cut-down version of a Linux operating system, and you just add applications to the image. And basically an image is a template, and then you provide a set of operations which builds on it. So you just say, okay, I want to add this, install this software, I want to do this, do this, do this. And it basically adds layers to the container, and then you've got your fill image which can then be run. They can have all sorts of things. You can run them, start them, stop them, delete them. They're all good stuff. So the images are built in layers. Each is a file system. It's a union file system. So what will happen is, if you go to Docker Hub and pull, say, a MySQL image, you will see it'll do a series of downloads, probably about maybe 6 to 10 separate downloads. Each of the downloads is a separate layer on top of the container. Does it support HTTPS? Yes, it does. You might need to do some configuration for configuring HTTPS, but yes, it does. One thing we will be doing actually is building a container which is an SSH server, so we can connect via SSH to it. So yeah, it pulls the base image, it pulls the layers, and it does the downloads in parallel. And then when they're all there, it just builds it all together into the base image as a single, what looks like a single unit, but it's actually layered. And so if you do one thing that's very powerful is if you make a slight change, it won't have to download everything, or if something slightly changes. So to give an example, I was trying to build an image, and as inevitably I made some mistakes in the configuration when I was trying to build it. And so when I made changes to my configuration and did a rebuild, it didn't have to go and fetch the bits it had already got. It had cached them effectively. So that meant the actual bandwidth and download that was required was minimized. It only downloaded the things that I'd added which hadn't already been done, which is really neat. So you have an image, and you use the docker run command, which creates a container. So basically the image is read-only, effectively, and the container is a copy of the image, which is an actual container running the file system. So when you say run, it'll first of all look for a local copy. If it doesn't find it, it'll go and search for it. And the container is created from the image itself, effectively as a separate file system. It adds a write layer to it, the top of the file system, so that you can make changes to it. It also creates a network interface and assigns it an IP address. The way it actually works is the Docker daemon acts as a gateway to a private internal network on your machine. It's an internal subnet, and the containers are attached to that subnet. But we'll look at networking in more detail later. It's actually quite powerful. You can also connect optionally the input, output, and error streams, so you can interact with the container if you wish, or you can run it as a background process. So the Docker, whenever it's run, the Docker container just appears as a child process. So this shows the daemon process here, which started with certain options, and then process 1410 is a child of Docker, which is the container running, in this case, a shell, which is one way of actually starting containers and quite powerful. So to run an image, it has to be on the computer, and so Docker has its own little collection of images, and if it hasn't got one, it'll either need to be created locally or pulled from a registry. And the pull just simply does a transfer of all the layers and puts them together into a cache, and then you run them to get the containers. So this is the example that's shown there. We wanted CentOS. Every single container usually has a :latest version. You can specifically ask for a version, so you can say I want CentOS version 7 point something, and it will fetch you that particular version of CentOS. And then you can run that container. And what you do is, the container will have some kind of default program which is configured into it, which will run. So if you just run it as a background process, it'll fire up some application which the container was built to do, whatever that might be. You can, in the case of, say, a CentOS one, or any of the containers, you can specify a command. So if you go docker run CentOS latest who am I, it'll create a container from the image, start it up and run the who am I program, and it'll then exit. And the same with any other command. So you can run a single command like this. Not tremendously useful, but it shows you the principle. Typically, you'll be running a real application, or quite often you'll run a shell so that you can interact with the container itself and make changes to it. So the way to do this is to run it interactively. Docker run -I keeps the standard input stream open, so you can use the keyboard, and -T allocates a TTY device, which means you can actually interact with the TTY drivers inside the container. And you normally go docker run -IT or -TI, specify the image, and specify the path to a shell. And that will actually run that CentOS container and give you a shell prompt. So you get the hash prompt as a root shell. Incidentally, the processes inside the container, your bash shell will be process number 1 inside the container because the process IDs are mapped. So process ID 1 in the container will map to process ID something else in the actual host operating system. You can do some interrogation. If you do a docker ps, it'll list all the running containers in your machine. And the container will be given a name. By default, the name is quite comical, but you can specify an actual name. You can also do a Docker stats, which shows you the resource usage, and you need to terminate that with a Control-C. So it's something to try playing around with. So it's very useful. I always do this. Docker run -IT --name, and then give it a sensible name, because then you can use that name to control the container. So that's the first one's running the container. You can stop it using docker stop, and you can remove it. Docker rm deletes the container itself, which you probably want to do quite a lot of the time because you just throw it away. We'll talk about external file systems and what happens, because when the container is destroyed, everything that goes with it goes as well, unless you've attached some external storage, which we'll look at. You can also attach to a running container. So, for example, if you're running one container interactively, like the first one, if you go to a second terminal and go docker attach CentOS, it'll attach your terminal to it, but you actually got the same session. So if you type into it in one terminal, you'll see the output in both, because it's effectively both attached to the same container. And there's this magic keystroke Control-P, Control-Q to detach from the container, leaving it running. So that means you can effectively walk away from detach yourself from the container and then reattach yourself later on, if you wish to. There's docker stop for terminating containers. You can optionally give it a time interval, and say main process ID 1, which is not in it. It's the main application started in the container, gets a term signal, and then after the interval it will get a kill signal to make sure it goes away. You can pause the container as well. That basically puts all of the processes in the container to sleep. It doesn't use the standard Unix sig term mechanism because of the process failures. You might be able to see them. It uses a control group freeze mechanism, which basically all the processes in the C group and its child groups are put to sleep without the processes knowing about it, and then you can resume them if you wish to with the unpause. When a container terminates, it actually doesn't go away. It just goes into a stop state. If you do docker ps -a, it'll show you all of the containers, including the stopped ones, which is very useful. And you can restart it by doing a docker start, and you've got the option of connecting the input and output streams to it. Removing containers, you just do docker rm CentOS in that case. If the container's running, it will refuse to do it unless you add the -f switch to force it to stop. ps-aq command shows just the container IDs. So that command at the bottom, docker rm $docker ps-aq, effectively deletes all the containers on the current machine. You can run them in the background by using the -d for daemon switch or detach switch, and you can send signals to the container as well using the docker kill. So let's look at Docker images. and work with the images themselves. What are they? So Docker has a number of images. The Docker Hub is a huge repository of bits of images for Docker, basically. And there's a lot of them up there. And you can usually find something that is a good starting point for anything you want to build. So you've got many versions of Linux, and you choose the version as well. So CentOS: latest will give you the latest version of CentOS, which can be used as a base. So any of the Linux distributions can be used as a base image. So the one we used was Alpine, which if you noticed was very, very small. That is a one that's been specially built to be very, very lightweight, whereas say CentOS or Debian or any of the others will have a fairly complete core of the operating system. It won't have any of the graphics. It'll have all the utilities to be able to do development and work it within the container, whatever you want to do. You can do a search, Docker search CentOS, and it'll give you any possible match that it's got on the Docker Hub. You can also go to the website and have a look around on the website to try and find what's available. So, installing software. Once you're inside the container, what you can do, there's actually two ways of building an image. You either do it with a build process, which we'll look at later, or alternatively, you go into the image like you did with the shell and just add the software you want. So you could go into the container and do yum or apt-get, depending on which flavor you've got, to install the software you want. The problem is you often end up with a lot of stuff you don't want. So for example, I was trying to build an image which had got the Maven build tool in it, and Maven is basically a Java application, and so Maven is dependent on Java, and it pulled in the OpenJDK, which I didn't want because I wanted to use the Oracle Java, and so using yum it didn't work, so I had to install it from a tarball or directly from an RPM or .deb package, which you just download. So one thing you can do is you can do a build by you getting the appropriate document, like the tar file, from the net, or alternatively you can provide a directory full of files which you can access. So we'll look at doing that later. So it's often better not to use yum or apt-get unless it's something fairly simple like the net tools for the ifconfig command. You wouldn't want to do it for a substantial application like Maven. So if you go Docker images, it shows you all the available images, and Docker RMI removes an image. It deletes the image from the local repository. So if you go Docker images, it shows you all the available images, and Docker RMI removes an image. It deletes the image from the local repository. So the CentOS base image, if we use that, it's pretty cut down. So I went in there and I wanted the which command to find out where the tools were, and also wanted the ifconfig command to see what the network configuration was, because it was quite important to me at the time. So I had to install it. So I connected to the CentOS latest and did a yum install. The -y switch basically means you don't have to answer yes to any of the questions that yum normally wants. It just automatically says yes to everything that the yum command says. And so we installed the which program and the net tools, which contains the ifconfig. So that's one way of adding packages, by just going interactively. So you can then do a docker diff, and it will tell you which files have changed. You probably get a fairly long list from that. And then what you can do is you can commit the container to an image. So what that does is we ran the container and it exited. So the container was still there, but it was in a stopped state, which is what it needs to be. We did a diff to check what was there, and then we did a docker commit on the container, the stopped container is called CentOS, to create an image called CentOS-net. And that basically turned the container into a read-only image with another layer added, which is the stuff we installed on top of the existing CentOS. And then we can remove the container as we no longer need it, and then we can run the image just like any other image. Run the image as a container, in this case running it interactively. The --rm option on the run command says to delete the container on exit. So if you're just doing something like looking at the configuration or something like that, just having a look around without making any changes, it's quite useful to use --rm because you don't have to worry about deleting the container afterwards. But if you want to do something like do a build, change something and then do a commit, you obviously don't use the --rm because you'll delete the container you want to commit. You can inspect the layers of the images using Docker inspect. By default, Docker likes to use JSON documents, JSON arrays. It uses it for both reporting and for configuration sometimes. And so you can use it on both images and containers. So you can get the size, you can get various things. If you put the -rf switch, it formats the JSON, it extracts the JSON fields with a certain matching pattern. So that's the inspect. Now, we don't really want to do this manual approach. We want to automate. This is what it's all about, isn't it? With DevOps, it's all about automation, really. Don't have to redo things manually. So how you create an automated build is this. You create a directory anywhere you like, and you put any files that you want to use for the build. This doesn't include stuff that you grab from the network. It's just files that you want for the build. Then you create a file called Dockerfile, which defines the build process. And then the directory becomes what's called a build context, which is basically a build context is a Dockerfile follow plus any associated files required to make an image. And then you build it. And each command in the build file, the Docker file, adds a new layer. And it actually creates, when it's doing the build, it creates containers for each command in the Docker file. It creates a new container and effectively then moves that on to become the next layer of the image, and then you end up with the final image. So if your Docker file's got a lot of commands in it, you'll end up with a lot of layers. So you'll find that a lot of people will write the file where it uses the command concatenation $& to execute multiple commands at the same level, so that one layer is actually the product of multiple commands. So if you wonder why there's lots of $& in a Docker files, that's the reason. So every Docker file starts with from, followed by the name of an image, and that's the starting point. So the build will fetch that image if it doesn't exist on the local system. You can specify a maintainer, which has got the email address of the builder. You don't have to do that, but for the sort of ones that are put out on the net for general usage, you probably want to do that. There's a shell command defines which shell to use. You often don't do that very often either. It can be done in either form. This is a kind of JSON form, which is one way of doing it. It defines, in this case, the default shell to use. It uses the JSON form in the Docker file. There's two forms for most commands, the JSON form and the sort of more straightforward form. So then you can use the copy command, and this is inside the Docker file. What it does is it copies files from the local directory, which is the build context, and stores them somewhere in the container. So in this case, what I'm doing is in the build contents, I've got a version of the Java RPM. I copy it to the temp directory inside the container. So remember, the source of a copy command, the left-hand side, is always a directory in the directory. You can use wildcards as they've done there, so anything that matches. Destination directories end in a / and they can create the directory if it doesn't already exist. So there's the add command, copies things into the container as well. Again, they're going to be in the build context. You can have the wildcards as well. It's just another way of doing it. But the add can use remote URLs rather than just files. That's the difference. And then the run is probably the most common one. What that does is it actually executes a command inside the container that is being built. Okay, remember it's building layers of images by creating containers, and these commands are executing the containers. Each of the run commands will generate a new layer and a new container. So we're doing a yum install which will go to the network, obviously. We're doing an RPM install from the file we copied to the temp directory, and we're also doing a run which is doing a CD and a link to, in this case, create a symbolic link called maven/op, which points to the actual installation. The commands mustn't block, which is important. And so you have the -y switch on RPM on YUM stops it from asking you if you want to do this. The commands mustn't block, but the multiple commands can be separated by a semicolon or a double ampersand. The difference is the semicolon will execute always. If you use a double ampersand, as in the Unix sense, if the first command fails, the second one won't get executed. So you'll properly use the double ampersand rather than the semicolon form. The docker env command creates environment variables in the image. So when the image is created and turned into a container and sort of fired up, these environment variables will be set. It's the equivalent of pushing them into the etc. profile. So this is setting up the Java home and setting up the path environment variables. The command, or CMD, defines the default application. So you typically have one command. You can have multiple ones, but if you have a command there, if you run the container without specifying a command after the image name on the run line, it will execute that when the container actually runs. Obviously, the command wouldn't normally be a shell. It would normally be the application that the container is providing. So the build process works like this. You have the build directory, which is the build context. When you do the Docker build, it basically creates a container, and the build context directory is attached to the container as a mount point. We'll see the details of this, how it really works later on. And so effectively all the directory contents are visible into they're copied to the daemon and all visible in the container that's been made. The Docker script, Docker file script is there, must be there, and you need to create a tag for the target image, and a tag is the name of the new image. So we notice that we have CentOS as the base, so I created CentOS Java, which is the CentOS plus Java, and I'm specifying the version is :latest. You can specify a version number if you wish. And so you specify docker build -t and the tag name, the name of the new image, and then the path to the actual build context, which I usually have as dot, which is the current directory, obviously. All the individual commands in the Docker file are in uppercase, and they're usually 3 letters long. Now that you've understood how to work on Docker images, Randy will explain how to create a Docker container containing the Alpine Linux distribution with SSHD through a demo.
Welcome to DevOps Lesson 2, Lab Number 2, Docker Images. Let's go back to our terminal, and in this lesson, this demonstration, we're going to create an image that contains an SSH server so that we run it in the background. We'll be able to make secure connection from our client to that container. The first thing we need to do, though, is to make sure that we have some keys generated. So you do that by saying ls to list in your home directory the contents of a .ssh directory, dot meaning hidden. And we see that we have authorized keys. That means we don't have the requisite keys. So let's generate those. We use the SSH keygen program, and we want the type RSA. This is where we want them stored: home, student, hidden directory, SSH, and by default it's ID _ RSA. We're not going to use a passphrase. And there our keys are generated. Let's double check that by doing the list of the directory. And there we see them. ID _ RSA, which is the private key, and ID _ isa.pub, which is the public key. Now let's go back to our home directory and type clear. Next, we want to prepare our computer to build an image. An easy way to do that is to create a directory focused on that task. So we're going to make a build directory, and then we'll enter that directory. Next, what we want to do is copy the key that we just generated. We want to copy the public key. So we're going to say copy from the root in the .ssh directory, the id.rsa.pub file. And we want to copy that into a file name authorized keys. That's because we're going to put that file, authorized keys, into the image that we're going to create. And that will mean that that particular container running that image has a public key for our pair. So we can use the private key to communicate with our public key and create a secure connection. The reason we're copying that into the build directory is that the build directory is the context in which we're building an image. We can copy files, we can create a Docker file. Let's actually touch that. And a Docker file contains the directives for creating an image. So let's edit that file. So here we are in the Nano editor. The first thing we do in this Docker file, and remember the Docker file defines a set of steps that Docker will follow to create an image. The first thing we want to say is, what is our base image? And we want to use Alpine, and the tag we want to use is latest. We want the very latest version of the Alpine image. Then we're going to instruct Docker to run a command, apk update. APK is the package manager for Alpine. So we're saying to it, please update your local cache so that we can make sure that we've got the latest versions of the programs that we want to install. Next thing we want to say is apk add open SSH. We want the open SSH package that contains the SSH server. Then we're going to say run add user. And I'll just type this in. You can see what the result is going to be. We're going to create a user, and notice that we're going to use an amper. That means continue on with the command, but only continue on if the last command completed successfully. If it did complete successfully, we're going to say mkdir make the directory home student.ssh, and then also echo student : student, and pipe that to ch password.
What is a Docker registry? A Docker registry is a location, usually on the internet, where Docker images are stored. A registry contains a number of repositories. Each repository contains different versions of a particular type of image. Registries contain many different repositories. One major issue about using Docker is that many of the images come in a lot of different versions. So typically a registry will have maybe 10, 20, 30 different versions of the same image. You need to choose the correct one, so it's quite important to choose exactly the right image. You can specify the version number when you pull the image from the registry. There's also a special type called latest, which means you always get the latest version of the image from the registry. And the problem is with Docker is getting the right versions. So what we do is we have these concepts of registries which are used to host images, and so you can go to a registry and get the right one. And so you have to think about various things like, do you really want to put your image somewhere in the cloud where everybody can get to it? Things like access control, and you've got to think about where the actual registry is going to be. So the registry is actually a service. It is actually usually a Docker image. A registry is a service used to manage and distribute images. It is based on a description of the image which consists of the image name and a version number. Registry is a manager of repositories, and a repository is basically all of the versions of the same image. So typically a repository only contains one image, but it contains multiple versions of it. You have the idea of a tag which tells Docker which repository to use and which image to use. Docker Hub is the default registry. Docker Hub has a default root namespace for all official images, so you don't need to specify the name of the namespace to get to an image. Just use the name of the image, the version number is all that's required. The root images on Docker Hub include versions of supported Linux distributions. All the popular Linux distributions are there at various versions, including the latest version. So, for example, the NGINX image, which is a web server, can be addressed in several different ways. It can be addressed with the full name of the Docker Hub plus the image, the version number, or it can be just simply the image name, version number. Labels. To save an image in Docker Hub, you need to define a label. The label comes immediately after the URL for the Docker Hub itself. The https://hub.docker.com. The first thing after the slash, in this case the R, is the namespace. So this can be either underscore for Docker Hub, which means it's one of the standard images, or R for user, which means it's one of the user-defined images used by one of the clients of Docker Hub. After the R comes a slash, which is followed by the username or organization of the user who provided the image. After that is another slash followed by the name of the repository item. So in this case it's netkernel-se is the name of the image. After that can come colon followed by a version number, which is often latest. It's not the only one. There are several. Google has the container registry as part of the cloud platform. It's got good access control and security. Amazon have got the container service. There's an organization called Key, which has got free plans and pay-for plans. You can set up your own registry, and there are others as well. So anybody can set up a registry if they wish to. In addition to the standard registries, you can also have a private registry. Anybody can create a private registry. They can either create it on their own machines or on the cloud. Private registries are very useful for storing images which you don't want to make public. So, for example, an organization would store all their internal images on a server inside their own network. Automated builds work in conjunction with a Git repository. What happens is that your Docker Hub account is connected to one of your GitHub accounts or other Git accounts. So what happens is you have a Docker Hub account where you store your images. You also have an associated Git account which is one of yours as well. You connect the two together. So rather than store the actual images in Docker Hub, what you do is just configure a Docker file which will build a Docker image, check that into the Git repository, and Docker Hub will automatically extract the Docker file from the Git repository and build the image for you. This is the preferred solution, and some accounts require this to be the case. The whole idea being that you don't build the images, Docker Hub does. So you could easily set up a repository in Docker Hub. You need to create a user, log into it, and then choose a namespace, choose a repository name, and set its visibility. So it's very easy to do. You do have to pay a certain amount depending on how many repositories you want and how many repositories you want. Because remember, a repository is required for every single image you want to store for your organization. And you need to log into the registry and the first time you do it, it'll store your username and password in a config file, which is used for subsequent access. Now, images need to be the same name as the repository, because the repository only contains one type of image. So you can commit an image to the Docker Hub registry name, or you could do it to another name. Okay. So you can use a new tag when you commit an image. So this one, creating an image, which is basically creating a Java image from a Docker file called Java, and then we commit it. And then because there's something slash in front of the name, that puts it to a particular registry. The name of the repository is question, and then you've got the version number. And then you just push the image into the repository with the right name. And you can use the image tags as well when you use the Docker pull command. So you can pull your private image from the Docker Hub. Images can be deleted from the command line, which removes the image from your local disk. Docker Hub doesn't allow images to be deleted at present. You can't delete an individual image from Docker Hub. What you can do is delete the entire repository from the settings menu on Docker Hub, which deletes all the images associated with that repository. So private registries. This is good. They've got the local image cache, so everything's quite quick. You can share images between teams in your organization, and you can choose to store images based on, say, development, UAT, production environment. And of course you can guarantee the registry is going to be available, because some of the other ones, even the commercial ones, might cease to exist. Oh, the field/something was that's specifying what the repository is, so it's probably a local one, but it could be one on Docker Hub if it got the right name. Yeah, the actual thing that goes before the image name identifies the repository, but it will check Docker Hub if by default, unless you're very explicit about it. So how do you create a registry? Well, there's one thing you can do, is that Docker Hub contains containers or Docker images which contain registries. And so you can just pull a registry image from Docker Hub, and that's the starting point for it. So you can now run the registry image as a container. You run it as a daemon process. So the -d switch, remember, runs it as a background process. The -p maps the port 5000 on the container to port 5000 on the host, which means that it's accessible from the local machine, and any machine that can get to that address on the particular computer. Specify the name is registry and execute the container registry. So that sets up your registry. Port 5000 is the default port for a Docker registry. And so now the registry is identified by hostname : port name and port number. And so you put that as the registry prefix. So here is an example of, we've got our local registry. And so what we do is, once we've got the registry set up, we can pull an Alpine image from Docker Hub. Then we can do Docker tag. And what that does is effectively creates an image with a different namespace. So it creates another image which has got the namespace localhost : 5000 called Alpine : latest. So then when we push localhost : 5000 / Alpine, it pushes that image into our local registry. And notice the name must agree. The thing before the slash must agree with the name of the registry, which is why we had to create another image from the Alpine one to the one that uses our local repository prefix. The default registry needs some configuration. Now this is fairly standard. Many images do this, that they specify, they're configurable by specifying command line options when you run the actual container. So you can specify environment variables using -e on the run command, or alternatively you can override the configuration file. So the Docker registry has a YAML file which contains the configuration. So what that command there does, we'll see this command in more detail later. The -v command says take the file /data/config.yaml on the local machine and copy it to effectively mount it onto the container as /etc/docker/registry/config.yml. So that means that when the container's running, it's using your config.yml, which sits over the top of the existing one and replaces it effectively. So effectively what you've done is mounted a file into the container to make that work. But that gives you a good way of doing that. The V is for volume, which is basically mounting a local file or file system into the container at a well-defined place. When you install a registry which you've downloaded from Docker Hub, you need to make some changes to the default configuration. For example, image needs some external storage for storing the actual images in. Otherwise, when you delete the container, you'll lose all the images. You also need to switch on authentication. By default, anybody can store or retrieve images in the registry without any kind of authentication whatsoever, so typically you need to set up some kind of username password system. By default, the search facility is disabled. This means you can't search the repository for images. You need to switch this functionality on to make it usable. The configuration files for making the changes to the registry configuration are complex. There are sample files available. They are stored in the Docker Git repository. There's another way of doing it. If you want to, you can use a Docker Registry RPM package. So if you've got a Red Hat flavor of Linux, like Red Hat Enterprise, Fedora, or CentOS, you can build an image from the RPM. So you could actually install it locally on the machine if you prefer, or you can build a container image, build an image from the RPM and run a container from it. And it's written in Python, and it uses the unicorn, the so-called green unicorn, Python HTTP server, because the repositories are basically web servers with the facility to store, upload and store and deliver images. So you can do yum install Docker registry either on your local machine or on a standalone machine or in an image. Then all you need to do is edit the Docker registry.yml file to set the configurations that you want for the registry, and then just run it. And this is showing how to run it on a Red Hat machine, either in a container or as a standalone on a normal installation of Linux. The Docker registry package can be installed in a Docker container. There are a few conditions and limitations on these. First of all, it needs to be based on a suitable image such as CentOS. Any Linux distribution will work as long as it's supported. The registry can't be run as a normal Linux service which is started at boot time, because much of the boot configuration software is missing from Docker containers. They're cut down versions of Linux file systems. So you have to start them as a daemon process rather than a service. It's also not a good practice to try and run services, as containers should only run a single application. So what is important is to write a script to start the registry. This must set up a few things. It must set up environment variables so that the registry is correctly configured and knows where its files are. You then need to execute the web server. This is the Python program gunicorn, and it has a large number of parameters. So the script here is what's the start point of the container. This script is executed when the container which starts up the registry service completely. gunicorn is simply a web server. It doesn't come with a registry in its own right. So the steps simply pull an image, add the registry layers, install the RPM as necessary, the Docker file and all that, and then just build everything and commit the new image. So there's the steps that we just went through. When you build a registry image, the first time you run the container, it's a good idea to run it interactively. So then what you can do is you can have a look around, see what's going on. You start the registry as a process, and then you can start to you run the registry as a background process, and then you can start looking what's going on, look at the log files, look at the ports on the machine, and everything like that. Make sure everything's working correctly. Once it's up and running, you use Docker search, Docker push to access the registry. So that one would show nothing, then the Alpine being pushed in, then the search would show Alpine as being in the registry. With this we complete the concept of Docker registry. Now Randy will explain the steps involved in creating and using Docker registry with the help of a demo.
Welcome to DevOps Lesson 2, Lab number 3, where we take a look at the Docker registry. You've learned that the registry is a location from which you can pull images. And you might guess that it's also a location to which you can push images, and that's entirely correct. The registry we've been using is a public registry provided by the folks that have authored Docker. But while this is convenient, you may need to have your own private registry. You've got private code, and only you should be able to pull it down. So what we're going to do is we're going to take a look at how to run a Docker registry, and in a bit of recursion, we're going to use an image, a Docker image that contains a Docker registry. So let's go to our terminal. And the first thing we're going to do is pull down this image. It's called registry. And we want the second version, tagged 2. And that didn't take very long. The first thing we want to do is pull down the registry image. And it's called registry. We want the second version, so the tag is 2. And notice it's coming down in layers. And as we've done before, let's just check images. And there it is, coming in at 37.6 megabytes. Okay, that's great. Now let's run it. So Docker run in detached mode. And we're going to do a port mapping of 5000 to 5000. So it's the same port. We'll say restart equals always. And we're going to give a name to the container. We're going to call it registry. And the image, of course, is registry:2. So it's up and running. Docker PS confirms that it's there. Now we're going to pull another image. We're going to do this so that we have something to push into the registry. So let's start that. We're going to pull in a rather large one. It's Ubuntu. And we're fine taking the latest. The latest is always the default. So we'll pull that down. Takes a little bit longer because it's larger. And there we go. So let's look at the images we have now. We have the registry that we pulled down, and now we've got Ubuntu that's coming in on 100.
So the final section for today is Docker machine. This is actually really neat. This is where you can manage Docker instances on remote machines. Typically you have a machine, one particular computer which is nominated as the controller, and then all the other machines anywhere in the world, maybe in the cloud, can be managed by that machine. And you can do anything you like to their Docker instances if you've got the right permissions. So what we've done is Docker has a number of components. Now we've basically used 2 of them so far. There's Docker Engine, which is the daemon, which does all the work. And there's a Docker client, which is the Docker command line tool, Docker. So now we're going to look at another one called Docker machine. And so the Docker client can talk to all sorts of things and can be a client to any host, which might be anywhere. They might be in the cloud. They might be on a local machine. It might be in a virtual machine environment of some kind. There's lots of different places it can be. But what happens is that there's a Docker machine client which enables you to talk to the Docker daemon and configure it. In terms of Linux, Docker came out at a certain level. Docker machine is often a separate application. You may need to pull it separately. It's now available for all versions, for Linux and for Windows and Mac. It is available. Unfortunately, say with Mac, there is the issue that the Docker daemon can't listen on TCP/IP connections, so you can't administer a Mac Docker server remotely, but a Mac can be a client for a Docker machine and administer other things elsewhere in the net, in the cloud or on the net. So why would you use Docker machine? Well, basically to manage remote Docker hosts. So literally you could install and update and run Docker and manage it on a remote computer from your Docker machine host. On older versions, if you use the Docker toolset, which was used to be used for Windows and Mac, and for unsupported versions of Linux, then you actually use Docker machine to manage the Docker engine within the container. So Docker Toolbox, basically it requires Docker machine to issue the commands to the machine. It's the only way you can manage a remote thing, and a virtual machine is a remote instance. So Docker Engine is just usually referred to as Docker. It's the daemon which has it's basically a web service. It's got an API, and there's the command line client called Docker. Docker machine is its own command. It's called Docker machine. It also, if you install Docker machine, it also has a Docker client. So Docker machine is actually a separate package on some installations, or with others it's bundled with just Docker. And so it allows the Docker engine to be managed remotely. And it actually does allow you to install Docker on a remote machine, which is quite an interesting idea. It does actually work. I've done it. So basically what you do is typically you allocate a machine, a dedicated computer, which runs Docker machine, and there should really only be one for your particular environment. So you've got Docker machine and Docker client. It then talks across the network to other machines which run the Docker daemon, and they become Docker servers. And this can get really powerful. As we'll see later on, there's a thing called Docker Swarm where these things can communicate with each other, and you can do some really clever things. So to do this, you have to set things up. Now, there is a interesting thing that was added to Linux under the control of the NSA in America, security organization, called SE Linux. I don't know whether you've heard of it, but it's basically a kernel feature which, if it's switched on, it really restricts what you can do. The problem was with Unix Linux was that they considered root to be too powerful, because root is all powerful. So SE Linux was added to reduce the powers of the root user and others, and it can also cause all sorts of unexpected problems. Like, for example, most Linux distributions these days come with SE Linux not only installed but switched on, and if it's switched on in full mode, it'll stop things from happening. Docker does have SE Linux support there. You might have noticed SE Linux switch on the daemon line in one of the libraries. But if you have problems, switch SE Linux off, at least for test purposes, and by changing the SE Linux config file, disabling it and rebooting. And also be very careful about firewall rules, because I've wasted quite a lot of time working on this material, trying to get Docker to work, because the firewall rules were blocking everything for me, and I didn't realize that they were actually there. So I switched off the firewall rules and everything started working wonderfully. So there's a particular port, 2375, which you must make sure is not blocked. So then what you need to do is have a remote user on the machine which has sudo access without password. Now that sounds a bit dangerous, doesn't it? But because that means that user can get root access and do whatever it wants to do. And so you have to add that line to the etc sudoers on the remote host for that particular user. Then you need to do the SSH thing. You need to be able to allow the Docker machine to access the remote machine using SSH without a password. And that means doing the key stuff. You have to generate the keys and then copy the public key to the authorized key on the remote host, so that you can access via SSH without a password. Again, something which is a little risky from the security perspective maybe, but it has to be done to do that. And then you do this. This is one way of doing it. There's many different drivers for dealing with Docker machine, but this is the one that will work on certain operating systems. And so that's the generic driver. The support for the Docker machine varies quite a bit depending on which flavor of which machine you're using. It typically only works for certain flavors of Linux. So what this is doing is creating a Docker machine, and we're saying use a generic driver, specifying the IP address of the machine, specifying the remote user of the machine, and then specifying the key, the private key of the user, which you copied over to the other one. And then specify the HP at the bottom is just the name of the computer that I happen to be using at the time. What that will do is basically log into the remote machine, the Docker machine will, using SSH, and it'll create an instance of Docker. It'll actually install the Docker server and set it all up on that machine, which is really neat. And then you can do a Docker machine ls, which will show you all the remote machines which are set up. It gives you information. If you install Docker on a remote machine, install Docker engine on a remote machine, you can't see it from Docker machine itself on another one until you've told it about it, because it can't figure one out, but you can actually point it at one and say, okay, here is a Docker instance that's already been created, you can manage it for me. Docker machine has a number of drivers. These are for installing remote instances remotely. There are different drivers for the different cloud implementations, such as AWS and GCP. There is a generic driver for installing on remote hosts. It does not allow instances to start and stop, unlike most other drivers. Some common drivers are those for the Amazon Web Service and for the Google Compute Engine. For CentOS, I tried to install Docker on it and there were files missing, particularly this one. Without that file, Docker on CentOS will simply not start. I just put that file on the machine and everything was fine afterwards, but there are some bugs associated with certain distributions. CentOS is only partially supported apparently for some reason because of the missing script, but once that script's there, everything's fine. Okay, so this is the chapter on virtualization. We're finished with that. Come to the end. Virtualization is a great way of managing things. Great thing particularly for big companies where you need to roll out similar machines to different people in different roles. Then we got Google started the process of enhancing the Linux kernel, which was continued onwards. The control groups and other things, which made a fairly weak, insecure jail from chroot into a very strong jail, which is hard to get out of. Then we've got Docker has exploited that technology and become probably one of the most important tools for doing containers. And so Docker is getting increasingly popular in many organizations as the way forward because you just literally plug the images. And in fact, as we'll see later on, you can actually update the images dynamically. When they're running as containers, you can actually update the image and recreate the containers on the fly. The images are layered from a base image. Every time you add something, you add another layer to the image, which is good. Build them up and maybe have several different images on the way. The registries manage the images, and remember, a repository is the different versions of the same image within the registry. And we've got Docker Machine allows remote installation and management of Docker itself. That's the end of the session today. Thank you very much